What are the biggest debates in quantum physics interpretations? Imagine trying to understand the very nature of reality through tiny particles that behave in strange ways. That's what makes the debates in quantum physics so fascinating. These discussions focus on how to interpret what the math of quantum mechanics really means about the world around us. One big question is about the wave function. Does it representing something real that exists in space and time, or is it just a way to calculate chances of what we might see? Some scientists think the wave function is a real physical thing that changes deterministically. Others see it as a tool that only tells us about probabilities, not actual physical objects. Next, there's the question of measurement and what causes the wave function to collapse. When we measure a quantum system, it suddenly chooses a specific state. Some say this collapse is just an update in our knowledge, not a physical process. Others believe something physical happens during measurement that causes the wave function to change. The Copenhagen interpretation, one of the oldest, says the act of measurement causes collapse but doesn't explain how. It emphasizes that the observer plays a role in deciding the outcome. On the other hand, some theories propose that collapse is caused by physical processes happening in the environment or within the system itself. Another debate is about whether the universe is fundamentally deterministic or random. The Copenhagen interpretation accepts that quantum events are inherently unpredictable. But some interpretations, like the de Broglie theory, argue that everything is determined by hidden variables guiding particles, even if we cannot see them. This introduces a kind of hidden order beneath the apparent randomness. The issue of locality is also a hot topic. Albert Einstein believed that no influence could travel faster than light, meaning distant particles shouldn't instantly affect each other. But experiments testing Bell's theorem show that quantum mechanics predicts and experiments confirm that particles can be connected in ways that defy classical ideas of locality. This suggests that either the universe is non-local or that our ideas about reality need to change. Then there's the idea of many worlds. Instead of wave function collapse, this interpretation says all possible outcomes happen in separate, branching universes. It keeps the math simple and deterministic but means there are countless parallel worlds. This idea is very different from the view that each measurement results in a single, definite outcome. Some interpretations focus on the role of the observer or even consciousness. They ask whether the mind is necessary to cause collapse or if the process can be fully explained by physical laws without involving awareness. All these debates matter because they shape how scientists think about quantum systems. They influence how we develop quantum technologies like computers and cryptography. Whether the wave function is real or just a tool, whether the universe is deterministic or not, these questions guide the future of quantum science. In the end, the core debates in quantum physics interpretations revolve around what the math says about reality, how measurement works, whether the universe is deterministic, and how connected distant particles really are. These questions keep the field lively and open for new ideas, even after many years of successful predictions.